I'm only missing one. That's not too bad. Start the broadcast. Optimize for video on. Okay, I didn't know that. Okay. All right, gentlemen. So welcome. Let's see. We are rapidly approaching the end of this thing. It's we have like only 2 more weeks of new material, right? So we have this week where we work on section 3.1, and then we have next week where we work on section 6.4. Let me see. Announcements are things like, okay, so I went through my classes, and students that had an excessive amount of unexcused absences. I think I submitted their name for administrative withdrawal, but I put a caveat in there that anybody that wants to stay just needs to request to stay, and I'll forward the documents for them to stay. So we are missing one today. So if you have a classmate, or if you have a buddy that's in my class, and if they've been like removed and they want to stay, all they need to do is contact me. First, they need to send an email to me that says that's requesting to stay, and it just needs to have their first and last name with their M number, and then the course that they're trying to be added back to with the CRN number, right? And just have that email it to me, and then I can forward that to the registrar so we can make sure that people are added back. Yeah, and let me pull up a calendar really quickly. So we're going to be done pretty quick. So this week we're working on section 3.1, which is today and Wednesday, and then next week we'll be working on section 6.4, which are further topics in algebra. It's basically solving system of equations. The week after that, on November 21st, that Monday, I think we're gonna start reviewing for the final at that time. And then that Wednesday is the Wednesday before Thanksgiving, so more than likely we won't meet because it's going to be the holidays. And then after Thanksgiving, we have one more full week with this November 28th and 30th. I think November 30th is the last day of class. So we'll take each of those days to review an exam, right? So the final exam, you can anticipate it to be cumulative. Basically a little bit of everything from the beginning to the end. It should follow a similar format to how our exams 1, 2, and 3 did. It should become available on that Sunday, December 4th, right? So that the last day of class is November 30th. That Thursday and Friday, the reading period, we already don't meet on Thursday and Friday, but those should be the reading period, and then the following week are finals. So I think I scheduled your final exam to become available Sunday, December 4th at 11:11 a.m. And what that means is that we're rapidly approaching that hard deadline of December 9th at 11:59 p.m. So what that means is that, you want to get all of your assignments submitted. If you need support, you just have to ask. Hopefully you guys have been linking with the tutors and working together. I encourage it because I know how much of a hard time this gives a lot of students. And, you just need to try to get it submitted. If you're going back and you're just trying to improve your overall grade, I would encourage you to prioritize your old exams as they're worth nearly 80% of your overall grade. That's going to be the most bang for your buck, right? So just, working through the old exams, that's going to give you the most bang for your buck. The last thing that you want to prioritize are the old homeworks. That's going to be a lot of work for minimal points. Yeah, that's the long and short of that, right? So today we'll take as much time as we can to make our way through section 3.1. And so we're in chapter 3 of exponential and log functions, and we're only going to be looking at section 3.1 exponential functions. So a few objectives here. We'd like to define an exponential function. We like to graph exponential functions. We like to develop formulas for simple and compound interest. We want to understand the number E, graph the natural exponential function, and model with exponential functions, okay? Now, I'd like to introduce this one. I do like to introduce this concept with a story. And of course, this is going to crash on me, so I got to reboot it. Let's see. Just trying to add a page here. Okay, and let's go here. Okay, let's apply it. Okay. So I'd like to introduce the concept of exponential functions with the story of the invention of chess, right? So there's this story of the guy who invented chess, and so, you know, there was this inventor, he invented a game of chess, and he shows, or he presents it to the ruler, right? And so the ruler sees the game, he thinks about it, and he enjoys it. He was like, I like it. So he was like, okay. He offered a reward in his weight in gold. The inventor thought about it for a moment, and then he offered another suggestion for a reward. The inventor suggested, okay, on the first tile, how about you give me 1 grain of wheat. On the second tile, you give me 2 grains. The third, you give me 4, and then 8, and then 16, 32, 64, and basically keep doubling it until you get to the last tile. The ruler thought about this for a moment, and he agreed to these conditions, right? So let's just see how many grains of wheat did the ruler agree to pay the guy. Okay. So on the first tile, he agreed one grain of wheat. So this is going to be our N, right? He's going to do 1 grain of wheat. Here, let's do it this way. So on the first tile, he's going to do 1 grain of wheat. Notice that 1 is 2 to the power of 0. So we're going to make this 2 to the power of n minus 1. And then he has a total. We can call this the total. It's going to be 2 to the power of n minus 1, like this. So he has a total of 1 grain of wheat. Notice that that is 2 to the power of 1 minus 1, right? Okay, so that's the first tile. Let's look at the second tile. He's going to double it, so now he has 2 grains of wheat. Notice that 2 is 2 to the power of 1, right? And so he has a total of 3 grains of wheat, which is 2 squared minus 1. Okay. And then on the third tile, he's going to put 4 grains of wheat, which is 2 squared. And he has a total of 7 grains of wheat, which is 2 to the power of 4 minus 1. Right? You should notice something. On the fourth tile, if you double that, it's 8, which is going to be 2 to the power of 3. And he has a total of 15 grains of wheat, which is 2. Sorry, this is supposed to be 2 to the power of 3. And this is 2 to the power of 4 minus 1. Let's do a couple more. Fifth tile, 16, which is 2 to the power of 4. And he has a total of 31 grains of wheat, which is 2 to the power of 5 minus 1. Okay. So if you continue this pattern, the chessboard is an 8x8, has 8x8, right? So it's a total of 64 tiles, right? So then on the 64th tile, he's going to have 2 to the power of 63 grains of wheat. And the total grains of wheat is going to be 2 to the power of 64 minus 1, right? So this amount of wheat, let me see, let me give myself a little bit of space. So let's crunch this number. Hey Siri, what's 2 to the power of 64 minus 1?
2 to the 64th power minus 1. is approximately 1.8446 times 10 to the 19th power.
So times 10 to the 19th power. So we need to, let's move the decimal place 19 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, right? So let's see what number this is. It's thousand, million, billion, trillion, quadrillion, 18 quintillion grains of. Yes, you can't see it?
Yeah, I can see it.
Oh, go ahead. Did you have a question? Ali Oxenfree?
You said say it again?
You had a question?
No, I just can't see the presentation. It just says you started the screen sharing, but I can't see it.
Oh, okay. Let me see. Yeah, I don't know. It's been kind of acting up. Let me go like this. Start the broadcast. Optimize. Maybe that's what's missing though. Just let me know if you cannot see it again. All right. So this, yeah. So this ends up being 18 just over 18 quintillion grains of wheat. This amount of wheat is more wheat that exists in the world even to this day. If this amount of wheat did exist, I think the dimensions where it would fit just inside a silo. I think it was 25 miles by 25 miles by 1,000 feet high silo. Don't quote me on that last part, but you know, the whole point of the story was the ruler basically agreed to give up his entire fortune, right? And so when the ruler realized that he couldn't pay the guy, you know how the story ended, right? Off with his head, right? That's my understanding of how the story ended. But this was just a demo on how quickly things can grow exponentially. All right. So this is just a demo on exponential growth. Okay. All right. I think I just checked Zoom, so I think you guys are good there. So that brings us to, so now we want to kind of review some properties of exponential functions. A function of the form here, of this form, where the base is strictly positive and not equal to 1, is called an exponential function with base a and exponent x. And the domain is all reals, right? So before we were working with things that were like a power function, right? So we had things like x squared, x cubed, so x to some power. So this is going to be exponential because now the variable's in the exponent. And the base of the exponent has to be strictly positive and not equal to 1. We call these exponential functions of base a and exponent x. So in this example, we're looking at evaluating exponential functions, right? So for part A, if we do f of 4, that's going to be 3 to the power of 4 minus 2. So 3 squared is 9, right? No, that's not what I want. Okay. So then for part B, g of negative 2. So if we're doing g of negative 2, that's going to be negative 2 times 10 to the negative 2. A negative exponent means the fraction flips, right? So instead of being 10, it becomes 1 over 10. So this becomes negative 2 over 100. So then 2 divided by 100, negative 0.02. Okay. So then for part C, we're doing h of negative 3 by 2. So then that's going to be 1 over 9. Why is it? So that's going to be 1 over 9 to the power of a negative 3 by 2. A negative exponent causes the fraction to flip, right? So this becomes 9 to the power of 3 halves. So when we're working with a rational exponent, like a fraction in the power, then the denominator of the fraction serves as the index for our radical, right? So if we're dividing by 2, that's going to be the same as the square root of 9, right? So we can rewrite this guy as the square root of 9 quantity cubed. So then the square root of 9 is 3. 3 cubed is 27. Okay. Copy. Okay. And then for the last one, I would encourage you to just use your calculator. All right. So you say 4 to the power of 3.2. Okay. And you see the results there. So in this example, we're asked to graph the exponential function. All right. So then, one of the techniques that we have for graphing this is basically plotting points, choosing several values of x, finding the corresponding y, and plotting the ordered pairs. Let me check on you guys in Zoom. We are missing one student, but it doesn't look like he's here. Oh, okay. Let me see. I guess they got booted or something. Okay. Yeah, I'm still just missing the same student. Okay. So again, one technique we have, we're asked to graph this exponential function. So one technique we have, choose several values of x, find the corresponding y, right? So we would just choose, let x be negative 3, negative 2. We just choose these values of x, pass them through the function to generate the corresponding y's, right? So then once you complete this table, then you just plot the ordered pairs, x versus y. Plot these ordered pairs, right? So then, when you plot it, you get the image on the left. And then if you connect them with a smooth curve, you get the image on the right, right? So that's the general shape of an exponential function. It generally looks like this. When you're going off to the far left, y, as x goes to the far left, y tends to 0. As x goes to the far right, y tends to infinity. Y goes off to infinity. The x-axis serves as a horizontal asymptote, right? So what that means is that in the long term, the graph gets infinitesimally close to the x-axis, but it doesn't actually cross it. The domain of this, the very left to the very right, is all reals. So any x's you can imagine, there's a corresponding y in the exponential function. But the range, the very bottom to the very top, the range is from 0 to infinity. The open interval 0 to infinity. So what that means is that it gets infinitesimally close to y equals 0, but it never reaches y equals 0. So the graph lies entirely above the x-axis. Okay. All right. So we saw an example where we were sketching a graph of an exponential where the base was larger than 1. Now we're going to look at an example where the base is between 0 and 1. We're going to kind of do the same thing where we choose several values of x, right? And then find the corresponding y, right? So with this first value of x, notice it's a negative exponent. It's going to cause the fraction to flip, and we're going to have 2 to the power of 3, which is 8. 2 squared is 4, and then it just goes from there, right? I think you can handle that. Okay, so then once we have these ordered pairs, we want to plot these ordered pairs, and we get an image that looks like this once you connect it with a smooth curve. So this is an example of something we call exponential decay. With the previous example, there was exponential growth, where as we trace it from the left to the right, we get growth. It grows rapidly. But then this one, as we trace it left to right, it decreases exponentially like this. Okay. All right, let's keep going. So we have some properties of exponential functions. Oops. So let f of x equal a to the x, where the base is strictly positive and not equal to 1. The domain of the exponential function is all reals. So that means any x you can think of, you can find the corresponding y. The range of the exponential function is the open interval 0 to infinity. So in other words, the entire graph lies above the x-axis. Okay, so you've seen that already. Okay. So then if we consider f of x plus 1 over f of x, then that's going to be a to the power of x plus 1 over a to the x. But then the numerator, we can rewrite it in this fashion. So then this factor can be canceled by this, and we're just left with a. So then what this is telling us that, so the y value is changed by a factor of a for each unit increase of x, right? So every time x increases by 1, y increases by a factor of a. So then when that base is larger than 1, that's called a growth factor. It's going to be a. Again, same reasoning, because the y value is increased by a factor of a for each unit increase in x, right? So then that's like the normal exponential graph that we have. So then we say that f is an increasing function. So the graph rises as we trace it from the left to the right. As x goes off to the far right, y tends to infinity. As x goes off to the far left, y tends to 0. Okay. So for a between 0 and 1, the decay factor is going to be a, because basically the y values are going to decrease by a factor of a for each unit increase in x. So every time x increases by 1, then y is going to decrease by a factor of a. That's where we had the exponential decay function, where it was basically the regular function just flipped horizontally. This function is a decreasing function, so the graph falls to the right. So as we trace it from the left to the right, it goes down. As x goes off to the far left, y tends to infinity. As x goes off to the far right, y tends to 0. Each exponential function f is 1 to 1, right? So 1 to 1 in this context, 1 to 1 in this context, that means that every y corresponds to exactly 1x, right? So a function being 1 to 1 is the same as saying the function has an inverse. That's the same as saying the function passes the horizontal line test. And that's the same as saying, there's one more. What's the final one? It's 1 to 1, has an inverse, passes the horizontal line test, and every y corresponds to exactly 1x, right? We have examples. We can generate an example of a graph that's a function, but it's not 1 to 1, right? In other words, we can generate a graph that is a function, but it does not pass the horizontal line test, right? And so an example of something like that would be a parabola, a U-shaped curve. So notice here, we could find a y that corresponds to 2 different x values. So this is an example of a graph that's a function, but it's not 1 to 1. All right. So 1 to 1 just means that the graph has an inverse. The inverse function basically undoes, if you take the outputs from the original function passing through the inverse function, then it takes you back to the start. So passing the horizontal line test, being 1 to 1, having an inverse, and every y corresponding to exactly 1x. These are 4 different ways of saying the same thing, right? All of those phrases can be used interchangeably. And then algebraically, to show that a function is 1 to 1, if we equate 2 different y values, then we need to show that those are actually the same x value. But if this procedure falls where you start here, but you don't finish here, then we say the function is not 1 to 1. And again, 1 to 1 is synonymous with having an inverse, right? Having an inverse. Okay. So the graph of the exponential function, it has no x-intercepts, so it never crosses the x-axis. And I know this is kind of a lot, like this is just like an introduction to the concept, and it's kind of like a crash course going through as many of the properties of exponential functions. I want to say a lot of these concepts come out naturally when you start working examples. Okay, so the exponential function never crosses the x-axis as long as you don't manipulate it. There's no value of x is going to cause the y value to equal 0. Okay. Another property is the graph of the exponential function is a smooth and continuous curve, and it passes through these 3 key points, right? And basically, we're looking at when x is -1, when x is 0, and when x is 1. From 4,3 and 5,3, we conclude that the x-axis is a horizontal asymptote for every exponential function of this form, right? So it gets really close to the x-axis, but it doesn't cross it. And when you start looking at these graphs for exponential functions, it's going to look like they're touching, but if you were to actually zoom in, you're always going to find space between our function and the x-axis. As long as it hasn't been manipulated to a different form, it's the entire graph is above the x-axis. It doesn't reach 0. The graph of y equals a to the negative x is basically the exponential decay. Notice that the negative is inside our basic function. So the graph has been flipped horizontally over the y-axis from our transformations, from the discussions we had on transformations. So instead of exponential growth, this is going to be exponential decay, right? So the graph of y equals a to the negative x is flipped about the y-axis, right? Again, it comes out intuitively or naturally when you start working examples, okay? All right. Okay, so before I talk about interest rate, there's one other story I like to share, just to kind of break up the monotony of it all. So when I was a student, I was attending an honor society. When I was a student at Morehouse, I was attending an honor society meeting, and they did this presentation, and it was entitled "The Infinite Scholarship." And what it was, they were trying to do a fundraiser to earn. Let me see. They were doing a fundraiser to earn $1 million, right? That was their goal. And they had an interest-bearing account that earned 5% interest, right? And so what this was, even if you take the lowest form of interest that we have, which is called simple interest, it takes on the form I equals PRT, right? So if we just calculate the lowest form of interest, where the principal is $1 million and the rate is 5% annually, then the amount of interest the amount of interest earned each year in that account is going to be, you're going to have your 1 million. The rate has to be expressed as a decimal, so that's going to be 0.05, and that time is 1 year. Okay. So then if you crunch this number, this ends up being $50,000 a year, right? Which comes to about a little over $4,000 a month, right? So the idea was, with this thing called the Infinite Scholarship, the claim was that they had an interest-bearing account that earned comparable to 5% every year, and that's why their goal was $1 million at 5% a year ends up being $50,000 a year, which is about a little over $4,000 a month, right? So what happens, as long as you don't spend more than an interest earned, then you'll make $4,000 a month forever, as long as that account is active, right? So the reason I like to share this is because, this is like life transforming information. I know people that have had $1 million, but they didn't try to figure out a way to keep money coming in forever, right? And so it was like, one of my classmates donated $1 million to our high school, and would have been a more savvy move is if he had an account like this, that money could have still been clicking. It could have been money still coming in from that one maneuver. Instead of just giving $1 million, you set up an account like this, and then it'll be money for generations, right? So as long as you don't spend more than the interest earned, you get $4,000 a month, and that's at least with these standards, today's standards, that's you're not going to be living like lavishly, but it's enough to where you can find decent things for that amount of money, right? Um, and so what this is kind of like this is similar to like passive income. It's not 100% fully passive because obviously you have to do other things, but once you get it set up, it's passive in nature. And like other things that I studied that have that property, like another one is like dividend stocks. Now, one thing is I'm no financial guru. You definitely want to like sit down with a financial analyst and have these kind of conversations. So that way one day you will get a chance to like create these kind of things, and you need to be aware of it so that you can figure out, okay, how can we keep this money going for as long as possible? But with dividend stocks, what that is that basically certain companies will give you a return on like just having holding some of their stocks. So like every earning quarter, they'll take a portion of they'll take their profits and divvy it up, and give it back to their stockholders, right? And so just for holding their stock, they pay back. And I've met people that they claim that that's how they make a living. Like they own enough stocks of this company where they can make a living off of just the dividends that they get back, right? And then one other one that I want to share is like through property management or property ownership, should I say? There is a brother-sister combo in one of my groups where their father left them this apartment complex. I don't know how many units, I don't know how big it was, but the claim was that it earns $20,000 a month. He was saying that the property manager manages the property. They do everything. Like they, go through applications. They collect the rent from the tenants every month, and when people don't pay, they work to get them out and get people paying people in there. But as the owners of the property, they just collect $20,000 a month and go live their life. Like to me, that's what I'm striving for. And it's like, I don't know how much of it I'm going to be able to enjoy while I'm here, but that's something that I can leave on to a loved one. You know what I mean? As opposed to leaving nothing, leave something where it can take care of them when you're long gone. You know, and so eventually it comes to a point because whatever it is we accumulate and whatever it is that we do, we can't take anything with us. We leave everything here. So if you're going to leave stuff, why not try to leave something that can help as many people as possible, right? That's how I feel about it. That's one of my personal goals. So, so that kind of introduces like compound interest. We had the infinite scholarship, dividend stocks, and property ownership and renting it out, basically. Those are really types of like passive income, but it was inspired by compound interest discussion. So we'll take a few more minutes to kind of look through this. So we have this definition on the interest rate is the percent charge for the use of the principal for the given period. The interest rate denoted by R is expressed as a decimal. Unless stated otherwise, the period is assumed to be 1 year. That is, R is the annual rate. The amount of interest computed only on the principal is called the simple interest, right? So that's the lowest form of interest that we have. Okay, and so we saw a demo on the simple interest formula, which you see here, I equals PRT, where P is our principal, basically the initial amount deposited into the account. R is our annual interest rate expressed as the decimal, and our T is our time, typically in years, right? So for these discussions, it's in years. So let's take a moment to walk through this. Juanita has deposited $8,000 into a bank for 5 years, a simple interest rate of 6%. How much interest will she receive? What is that? That's so weird. I'm sorry, guys. How much interest will she receive, and how much money will be in her account at the end of 5 years, right? So here we're using simple interest, PRT, right? A. So the interest is going to be the principal, which is the $8,000, times the rate. Now the 6%, we have to express it as a decimal. So when you see 6%, you can look at that percent symbol as per 100, right? So that percent symbol, you can just switch it with per 100 like this. So then this is going to become 6 over 100, which is 0.06. Okay. And the time, I think, was 5 years. Hey, Siri, what's 8,000 times 0.06 times 5?
8,000 times 0.06 times 5 is 2,400.
Okay. And then for part B, how much money will be in the account after 5 years? So the future amount is going to be the starting amount plus the interest earned, and 8,000 plus 2,000 is going to be 10,400. Okay. You guys have any questions? Let's keep going. Okay. So then there's more, but we're almost out of time for today. So the compound interest formula, I'm going to pause on this one because there's a more accurate one. I'm going to leave this as an exercise. Let me see. And I want to take a moment to talk about this one. So this is our compound interest formula. So A is going to be the amount after T years. The principal is going to be our P, so that's our starting amount. The annual interest rate has to be expressed as a decimal. N is our number of compoundings per year, so that's how many times the interest is applied within a year. And the T is the time in years that this account is operating for. Okay. So with this last one, I'm going to leave this as an exercise for you guys. But the main thing that I want to share with you is like a primer, right? So if $100 is deposited into an account that pays 5% annual interest, find the future value A after 1 year if the interest is compounded with these different compounders, right? So, I have a pre-recorded lecture where, we only made it through about half of this because we only have, 50 minutes or so. But that's why I made my pre-recorded lectures, so you can watch those on your own. And then, so if the interest is applied annually, that means our N is 1. If the interest is applied semi-annually, that means N is 2. Quarterly means N is what? 4. Monthly, N is 12. And daily, N is 365. Okay. And so, you apply these to your compound interest formula to generate the results. Did you guys have any questions for me? Do you have any questions? Okay. Let me go ahead and make a copy of the stuff you saw me writing available for you. So when this bar finishes loading, you'll get a copy of anything that you saw me writing. If there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day, guys. Take care. Peace. Let's see. So hopefully, what was that? Hopefully you're able to see that. Like it's better to do the audio to get my attention because typing in the chat, I just check it randomly. But if you speak up, then I'm like, oh, then I can fix stuff. All right, guys. If there are any other questions,